Adding this to the Thermo review, it's not on the worksheet. You'll see this done with slightly different titles for the axes. You'll also see it called different things. It's often called a reaction energy profile. I've seen it called different things. And it shows the energy of the species as the reaction occurs. And so let's just put our reactants here. Let's put an R for reactants. If it's endothermic, the products will end up higher, like there. If it's exothermic, the products will end up lower, like here. And then it'll always be a hill. So for example, it might be a pretty significant hill like this, and then fade down to the products. Or there are times you might see barely a hill at all, but it always will be a hill. What you will never see is you will never see it just go directly from reactants to products like that. And the reason is because the particles have to collide with some amount of energy to react. They can't just react without no inspiration for it. So you must have at least some little bit of hill, whether it's endo or exothermic. Let's go back to a more traditional one that looks like this. There's two important things to remember. One is that from the beginning of the reaction, which is the reactants, to the top of the hill, that value here is called activation energy. It's usually denoted EA. And that's the minimum energy needed for this reaction to occur. If the reactants collide and they collide with this much energy, but they don't quite make it all the way to the top, what they will usually do is they'll just fall right back down to the reactants. So they never change. They started to, but they didn't have enough energy. The only way they can react is if they collide and have this energy, then they can make it over the hill and fall down and become products. Again, whether it's endo or exothermic. The other important thing to note is from reactants to products, this value here, that is delta H. That's the enthalpy. And notice the enthalpy does not care about the hill at all. It doesn't care how high it is. It doesn't care the shape. It doesn't care whether the hill has multiple bumps. Sometimes you might even see a hill go like this, and it'll have multiple hills as it goes on its journey. It doesn't care about any of that stuff. The delta H only says, what's the energy where you start? What's the energy where you end? And that actually is another way of saying Hess law. Hess law does not care about the path. It is not looking at any of this stuff. It just wants to know where you start and where you end. And if you start and end in the same place, it's going to be the same energy. There's some more details that we'll get into in the middle, like what is actually happening here. But that'll save. We'll do that when we get to what's called kinetics and how fast reactions occur. And so we'll save it for that. The only other thing to mention here is the way I've drawn this. Notice that this goes down. So this would be a negative delta H. If we had a positive delta H, the products would be up here, and the curve would still have a hill, but it would end in a higher spot. And in this case, that would be my delta H, and it would be a positive delta H, or endothermic. And that should be enough for this for now. Like I said, we will go into more detail on this when it is appropriate, and we'll talk about things like catalysts and things related to that.